All right, awesome, y'all. Um, okay, so let's start off. All right, is this working fine? If you have any problems with this, just type it in the chat. Hopefully y'all can see fine. All right, so today we're going over geometry, and our agenda is to go over angles and polygons, similar triangles, and then finally properties of a circle. So you will notice that we didn't cover any like area. I'm not going to cover any area or perimeter stuff like that. Hopefully you're learning this in school. The topics I'm going to be going over are typically going to be the topics that you find in later AMC questions, and maybe even like AMI or even like early USAJMO. Typically in like AMC8 or early AMC10, you'll find a lot of area questions, and geometry problems are usually just problems that make you want to like count. So I guess let's just get started. Again, Isabella is going to be your other moderator, and if you have any questions, just open the Q&A tab and she can answer your questions there. Again, if you didn't print out the handout from the website, you can do that now so you can follow along with us, but otherwise I'll have the question on my screen so you can follow along on paper. All right, so angles and polygons. First off, the sum of all the interior angles for an n-sided polygon is 180 times n minus 2. And this is regardless of what the size of n is, as long as n is greater than or equal to 3. So for example, a triangle has a sum of 180 for all its angles. A square has 4 minus 2 times 180, which is 360, and so on. So that means that for a regular polygon, for example, an equilateral triangle or a square, the common interior angle is the expression below. All right, so I'll take a minute to look at this. Hopefully this is a review. All right, now exterior angles are also pretty interesting. So if we look at the diagram on the right, we see that the exterior angle in this case is angle 4, or angle RQS. And this is formed when we extend the ray PQ out towards S. So one of these properties is that angle 1 plus angle 2 equals angle 4. And you can easily prove this using the fact that angle 3 and 4 sum up to 180 because they're on a line. And because angles 1, 2, and 3 add up to 180 because they're in a triangle, right? And another cool fact you should know, it doesn't really show up in AMC, but the sum of all the exterior angles of any polygon is always 360. So it doesn't matter how many sides you have, the sum is always going to be 360. All right. Similar triangles. Now I have to say similar triangles are the most important things that you will encounter in contest math. Basically any problem from AMC8 to AMC12, any geometry problem, half of them will be requiring either area or perimeter, and half of them are going to be requiring similar triangles. So you can detect these similar triangles by either looking at the angles or the sides. School geometry classes go over this. There's like angle, similarity, side, angle, side. But basically, if you see that two angles are the same, so in the diagram on the right, angle A and angle C are the same, angle B and angle D are the same, then you can say that these two triangles are similar. So what that means is that everything about the triangle is the same except for their size. So if you took one triangle, reflected it, translated it, and you just made it bigger or smaller, then you would get the other triangle. And you can also tell that they're similar if you look at their sides. So if they're proportional like in the figure on the right, then they're also similar. So similar triangles have proportional side lengths and congruent angles. All right. Now these are just so important, and at the AMC and AMI levels, you'll definitely find that these higher level questions definitely require you to be really familiar with similar triangles. And you need to be able to recognize where you would find these. Okay, so typically if you have parallel lines, you'll find that you can find some congruent angles if you draw a line going through it. So that probably invites you to look for some similar triangles to see if you can get some extra values based on the given information. All right, here's a list where you could find similar triangles. I would say that if you look at a problem and you see any type of triangle and any type of like intersecting lines, you want to first look at, well, are there congruent angles? Do we know the proportions of the side lengths? And if that's the case, then definitely go to similar triangles first. Okay, so with these two topics in mind, let's go to our first few questions. Okay, so this is our first question. The degree measure of angle A is, and we're looking for that. I'll take a minute for you guys to try this out. Look at it, think about what's the best approach to solve this. Okay, so let's see. First off, let me label these points. Let's call it C, B, D, E. Now, if we start off, we say, wow, there's a lot of ways to get started, right? But I'll go through two of the ways that I thought of first. So let's look at this angle right here. Now, we know that on a line, if there's two angles like that, they're supplementary, which means that they add up to 180, right? So we can say that this is angle AEC plus 110 equals 180. So this has to be 70, right? And now we know that the sum of the angles in a triangle add up to 180. So that this third angle inside this triangle right here is going to be 180 minus 70 minus 40, which is 70. And then since these are intersecting lines, then this other angle has to be 72. And again, with the same reasoning, we can find this angle ADC by doing 180 minus 100. So that's 80. And finally, angle A is 180 minus 80 minus 70, so that's 30. All right, that's one approach. Another way you could do it is by finding angle B first by using this big triangle over here. Right, we have one angle which is 40 and then one angle which is 100, so the last one has to be 40. And then now we use this big triangle. So one angle is 110, one of them is 40, so the last one, angle A, has to be 180 minus 40 minus 110, which is 30. All right, hopefully that was pretty straightforward. Take a minute to read this one and then see if you have an idea as to how to do it. Remember, you can use the Q&A feature to send your answers in, and Isabella can answer and tell you if you're right or wrong. Okay, so we're given CAT is 36, so let's just write that down. ACT is congruent to ATC, so this is isosceles, and that means that the angles are the same, and 36 plus 2 times any of these is 180, which means that each of these is going to be 72. So that's 72. This whole thing is 72. Now RT bisects angle CTA, so each of these is half of it. That's 36. This is 36 as well. And again, our final step is going to be using the sum of the angles, so that's 72 as well. All right. So hopefully that was straightforward too. These are typically questions that you find on early AMC8 problems. All right, here's our first question regarding similar triangles. Take a minute to read it. In triangle ABC, a point E is on line AB with AE equals 1 and EB equals 2. Point D is on AC so that DE is parallel to BC, and point F is on BC so that EF is parallel to AC. What is the ratio of the area of CDEF to the area of triangle ABC? Okay. So here we look at, well, we see triangles, right? And then we see parallel lines here and here. So we automatically think, well, I'm going to find a lot of congruent angles, and that means I want to look for similar triangles, right? And here's really apparent. Triangle CAB is similar to triangle DAE. And it's also similar to triangle FEB, right? All of them even look the same in the diagram. So now we know that triangle DAE is similar to triangle FEB. So that means that each of these side lengths has a ratio of 1 to 2. So I can say this is DA is some length x, FE is some length 2x. All right. Honestly, we don't even need to know that though. So if we want to find the area of CDEF, we can look at the areas of FEB and DAE first. So the area of FEB over the area of CAB. So this is finding what's the ratio between the areas of FEB and CAB. Well, this is going to be the square of the ratio of each of the side lengths, right? And for example, we could take FB over CB. For these similar triangles, you can look at the ratio of the side lengths to figure out what the ratio of the area is. And it's just going to be that square. So FB over CB is 2 to 3. All right. We don't even need to know the lengths to figure that out. So that's 4/9. Now we can look at the same thing, but for DAE. And this is going to be 1 to 3 squared, right? Because everything is 1/3 about that triangle compared to CAB. So that's 1/9. Now that we know this small triangle is 1/9 of the area, this medium triangle is 4/9 of the area, then this parallelogram over here is going to be 1 minus 1/9 minus 4/9, which is 4/9 of the total area. All right. Take a couple seconds to look at that. Okay. This one is a little bit harder. It's from AMC10. Right triangle ABC has AB equals 3, BC equals 4, and AC equals 5. Square XY CW is inscribed in triangle ABC with XY on AC, W on AB, and Z on BC. What is the side length of the square? Let me draw this out. All right, so AB is 3, BC is 4, and AC is 5. Okay, so let's get started. Well, it's asking for the side length of the square, so let's just let that be x, so we don't have to solve for it again. No. All right. AB is 3, BC is 4, AC is 5. So we know that this triangle, this big triangle ABC is a 3, 4, 5 right triangle, right? Now, we also know that this line WZ is parallel to XY. So what does that mean? That means that this angle is congruent to this angle, and this angle is congruent to that angle. So we know that triangle ABC is similar to triangle WBZ because of angle-angle similarity, right? So we have WZ is X, and we're looking for, let's say, WB. So WB over AB equals WZ over AC, right? Because that's the proportions go into play.
I didn't get that. Could you try again?
Let's see. All right. WB. So we don't know WB or WZ, but we do know AB and AC. So WB equals AB is 3, so 3 times WZ over AC, which is 5. Okay, so that's 3/5 X. Now, we can do the same thing for AW. I'm going to write it down here because I don't have space. So WA, it's the same thing. We notice that this triangle right here looks like the 3, 4, 5 triangle, but just at a different angle. So we know that the side lengths are still going to be in the ratio of 3, 4, 5. If this length WX corresponds to the forward length, then we know that the hypotenuse of this little triangle AWX is going to be 5/4 of that because it corresponds to the other one. So now we have AW equals 5/4 X, and then WB equals 3/5 X. And the sum of those two equals 3. So if we added those fractions together, that would be 37 over 20x equals 3, which means that's down here, sorry, x equals 60 over 37. Now there's multiple ways to do this. You could have done it by going on the bottom and using AX, XY, and YZ to find your side lengths. Any way is okay. Here's whatever you find first, whatever you find comfortable. Okay, so that's it for similar triangles and angles. Now let's go to properties of a circle. Okay, so we're going into territory that's between Amy and USA JMO now. So this is actually going to be really hard. I know a lot of you haven't done this stuff before, but hopefully you'll get a taste of what it's like in Amy. And this stuff is really going to help you, even with AMC level questions. Okay, so our first topic is power of a point. Take a minute to look at these diagrams and then look at the formulas. Just reflect on that, okay? Okay, so let's look at the first picture. We notice that E is a point inside the circle, and then points A, B, C, and D are all points on the circle. AC and BD are chords, and then E is the intersection. So what power of a point tells us is that the power of the point E is the same no matter how you solve for it. Okay, so imagine I chose a point E in there, and then I made two chords that intersect E that go through the circle. So it doesn't matter what these chords look like. It's always going to be the case that AE times EC equals BE times ED. Okay. Now, this looks really random, and you might be like, well, how do I prove this? If you actually want to prove, try connecting AB together and then try connecting DC together and look at the triangles AEB and DEC. You'll notice that they look really similar, or that they are similar triangles. Okay, anyways, so this is the chord-chord intersection variation of the power of a point. For the second diagram, you'll notice that A is a point on the circle, B is the tangent to it, so AB is the tangent to the circle. Now tangent means that it intersects the radius at a 90-degree angle, which we'll go over in the next slide. But anyways, we have C and D as points on the circle again, and then B, C, D are on a line. So power of a point still tells us that BA times BA, or BA squared, equals BC times BD. Okay, and this might make more sense if we look at the last diagram, where C is now the point that we're trying to find the power of, and we have points A, B, D, E on the circle. So power of a point tells us again that CB times CA equals CD times CE. Now imagine if you took the first diagram, you look at the first diagram, and now you just dragged E outwards. Right? You'll notice that it looks a lot like the third diagram. And that's basically how it is. Okay, so this is really useful in AMY level questions. You might not see any of it even, you won't see any of this in AMC8, but you will see this in AMC10 sometimes, and definitely in AMY. Okay. So tangent lines. Now these are interesting. So for every point outside the circle, let's say C, there's two tangent lines that intersect the circle. Each tangent intersects the circle exactly once. That's the definition of it. So for this case, CD intersects the circle at D, and CE intersects the circle once at E. And it forms a 90-degree angle with a radius. Okay, so that means that CD is perpendicular to DA, and CE is perpendicular to EA. And finally, you might have done this in geometry class, but the two tangent segments are congruent, so CE equals CD. And you can prove this by drawing in line CA, and you'll notice that triangles CEA and CDA are actually congruent. Okay, so we'll be using this in a couple questions. Surprisingly, AMC has a lot of questions that talk about tangent lines and circles. Okay, so let's do a couple questions with that in mind. So take a few minutes to read this and then try it out. I will say this is a really hard question, so if you can solve it, that's amazing. But I'll be going through it step by step to make sure that we're all okay with it. Okay, so let's go through what we have so far. We have triangle ABC, AB is 84, we have so far. We have triangle ABC, AB is 86, and AC is 97. So this is point A, point B, and point C. A circle with center A and radius AB intersects BC at points B and X. So let me draw that in. Oh, wow. Okay. So this is point X right there. Now we know that BX and XC have integer lengths. And what is BC? All right, so first off, we can tell that we aren't really given much, right? We only know two side lengths, 86 and 97. So we look at this third criterion, which is BX and CX have integer lengths. So we want to find a relationship that has BX and CX inside of it. All right, let me call BX, let's call this X, and then let's call the length of XC Y, okay? Now, we notice that B, all right, actually, let me call this M and N so there's no confusion. All right, we notice that BXC kind of looks like that previous diagram we had, right? Where C goes out from the circle and we're looking for the power of the point C. And let's say we did take the power of the point C. So the power of C would be, we take the length of BC, so BC, and then times, we go from X to C, so times XC. And then we can write BC as M plus N. And then XC is, of course, N. Now, we want to relate this to another power, right? We haven't even used the fact that AB is 86 and that AC is 97. But how do we do that? Well, let's draw on this line right here. So if we do that, now we have one whole line going from this point, M, this point, let's say P. So going from P to C, we have one straight line. And then let's call this intersection point right here, let's call it D. So now we have another way to find the power of C. Now we can do the power of C, let's just say that would also be equal to CD times CP, right, where P is this upper point. Do we know CD? Well, we do, right? Because AB is 86, which means that since it's a radius, AD is also 86. And we're given that AC is 97, so that means that DC is 97 minus 86, which is 11. Okay. At the same time, AP is also a radius, so that's also 86. So we can write CD as 11, and then CP is the same as PA plus AD plus CD, right? The sum of all those segments, the radius, and then that extra part over there. And that's 11 times 86 plus 86 times 11, which is, plus 11 is 11 times 183. Okay, so now we have that these two powers have to be the same. So we know that M plus N times N equals 11 times 183. So I'll give you 1 or 2 minutes to look at that and see if you understand it so far. If you don't, just ask some questions on the Q&A. Okay, so our last criteria was that bx and xc have integer lengths. So m and n have to be integers. Now we can look at m plus n by itself and then n by itself, and we know that they have to be factors of 11 times 183, which is 11 times 61 times 3. And at this point, it just became a number theory question, right? So we know that m plus n times n is some variation of 11 times 61 times 3. So we can kind of just guess and check. Let's say m plus n was 61, and then n was 3 times 11. And in this case, m plus n is 61, n is 3 times 11, or 33. And we see that this works because we see that m equals 28 in this case. And that means that, well, this satisfies all the requirements, first of all, because they're integers. And second, we have to check this triangle ABC. Is it actually a triangle, right? If it's actually a triangle, we have to check the triangle inequality, which says that the sum of two lengths have to be greater than the third. Now, that rules out the case that BC equals 11, because if I had a triangle with 86, 97, 11, that wouldn't even work, because 86 plus 11 is 97. It would look like a line, right? So we know that m plus n can't be 11. It can't be too big either. Otherwise, it goes over 86 plus 97. You'll find that this case where m equals 28 and n equals 33 is the only case that works. So we're done with that. So our final answer is we're looking for BC, which is m plus n. So that's 61. Now, you'll notice that this was a really hard question. And it should be, because it was a number 24 on an AMC10. Okay. If you have any questions, just don't be shy. Ask on the Q&A. We'll be ready to help. Our second question for this is externally tangent circles with centers at points A and B have radii of lengths 5 and 3, respectively. A line externally tangent to both circles intersects ray AB at point C. What is BC? So go through a few keywords here. Externally tangent circles means that these circles intersect each other once. Okay. And then the line externally tangent to both circles refers to a line that's tangent to this circle and that circle. So it kind of just lays on top of both. Okay, so this is hopefully the setup that you found. let me label these points. The centers are A and B, and this point out here is C. Okay, I'll give you guys one more minute to look at that. Okay. So from here, it's not too clear where to get started. So let me go to a slide. So we saw tangent lines for one circle, right? When we have tangent circles, a lot of the setups will look like this, okay? So two circles will be like that. They'll be tangent to each other externally. And then we can draw these external tangents, so DH or DG, and they'll intersect both of these circles once. So when you're solving these questions, they'll be asking for, well, what's the length of DA? Or maybe they're asking for DH or HG. And here, if you know both radii, then you know the lengths of AH, CG, and AC. And then at that point, you can use similar triangles to find whatever you're looking for. So let's go back to the question. Here we have that, let's call that D and E, those are the tangent points. We know that AD equals 5 and BE equals 3. So now we can find the length of AB, right? Because this is also 5, that's also 3. So AB is 8. Okay. Now we call upon the information we learned from the last slide, which is that they intersect the radius at a 90-degree angle. So we know that AD is perpendicular to DC and BE is perpendicular to EC. All right, at this point, we see, well, we have right angles, which are congruent. We have this angle that's common to both triangles BEC and triangle ACD, right? These two skinny triangles, they both have right angles and they both share this angle C. So what does that mean? Well, we have angle-angle similarity here, which means that these two triangles are similar, so their side lengths are also proportional. Now we're looking for side length BC, right? This length right here. We can write a proportion where BC over AC equals
I didn't get that.
BE over AD, because we're taking these proportional side lengths, right? Now,
I didn't get that.
Oh my.
Could you try again?
Siri just. Okay, so we have BC, we don't know BC, but we do have the other lengths. So BC equals BE times AC over AD by moving that AC over to the other side. We have BE equals 3. AC is 8 plus BC, right? If we split this segment into 2, we have one part over here, which is 8, and then the other part, which is BC, which we don't know, over 80, which is 5, right? So we can move this 5 over, multiply it to the other side. We have 5 BC equals 3 times 8 plus BC. So 5 BC equals 24 plus 3 BC. And then BC equals 24 over 2, which is 12. So that's the answer you should have gotten. Now in the homework, you'll see a lot more questions like this, so make sure that you have this process in your mind. I'll wait 1 or 2 minutes so you can write this down if you want to. The most important here is to remember the process, okay? As long as you know the process, then these questions, no matter what the numbers are, you should be able to solve. All right, down here, number 3, we have a situation with a circle and segments and triangles, so I'll let you read that and then we'll go over it later. Okay, so hopefully you read that and you drew a diagram. Let me draw this out real quick. All right, so we have a diameter and it's extended 3 units out. This is A, it's B, this is D, and we're given that line ED is perpendicular to line AD. So E, start there, and its length 5. It's a little off, should be a little higher, but there's no space. All right, so we have BD equals 3, and then radius 2, so that each of these are 2. Now segment AE intersects the circle at point C between A and E, so right here. It's asking for the area of ABC. Okay, I don't know if y'all knew this, but in USAJMO and USAMO, they actually give you a point for drawing a correct diagram. So just remember that diagrams are really important. All right, so our first step here is to look, well, how do I find the area of ABC? So we're given these side lengths, and we have these triangles with this circle, but we can't really relate triangle ACB to triangle AED yet, to the big triangle, because although we do know that angle A is shared, we can't say for sure that angle ACB right here is a right angle the way that ADE is. All right, so at this point, let's go back to the slideshow. All right, so for inscribed angles, we have ABC on a circle, and then O is the center. This property is that angle ABC is half of angle AOC, which isn't shown here, but you could think of it as half of the arc length. So this is super important, probably the most important thing for circles, at least in Olympiad geometry. But you might see these questions in AMC10 too. More commonly, you'll see the special case, which is when AC is the diameter. And then when AC is the diameter, well, we go back to the first equation. Angle AOC is going to be 180 degrees. Or we could think of it as the arc length of AC is half the circle. So that's 180 degrees. Now half of that is going to be 90. So we have that whenever AC is the diameter, angle ABC is going to be a right angle, okay? So this is super helpful, especially if you're looking for like similar triangles. They'll have this property that they're testing you on to see if you actually understand it. So I'll give you a minute to look at this. All right, so now that we know that, we can go back to the problem and say, well, AB is the diameter of the circle O, and C is a point on it. So that property tells us that by inscribed angles, angle ACB has to be a right angle. So emphasize that, that's a right angle. So now we can use similar triangles because we know that angle ACB is congruent to angle ADE. So triangle ACB is similar to triangle ADE. And what does that mean? Well, now we know that AB over AE, so the hypotenuse of triangle ABC and the hypotenuse of triangle ADE equals one of these lengths over 5. So let's just call that. Actually, either way, we know that this is the proportion in which these triangles are related. So if you go back to one of the earlier questions, you'll notice that we can take this proportion and then square it to find the ratio of the areas, all right? Because these triangles are similar. If you take the side lengths, square them both, and then divide them, you'll have this ratio but squared. So we know what AE is by using Pythagorean theorem. On this triangle, we have ADE. This is 5. This is 7. AE is the square root of 5 squared plus 7 squared, which is the square root of 74. So root 74 over here. And then AB, we already have is 4, which is the diameter. So that's 16 over 74. So we have this number. Now, what does this tell us? This is the ratio of the area between ABC and ADE. All right. We can get the area of ADE by multiplying this base by the height, which is 7 times 5. And then we divide that by 2, so 35 over 2. And if we solve for ABC now, we get that ABC equals 16 over 74 times 35 over 2. Wait a minute. Yeah, okay. And then we can cancel out a 2 over here from the top and the bottom. So our final answer is 4 times 35, which is 140, and then over 37. So that's our final area. So the last topic is going to be Ptolemy's theorem. And you can just read that. So it says that if I have points on the circle A, B, C, and D, we can call ABCD a cyclic quadrilateral. So that means it's inscribed in a circle. And this theorem says that AB times CD plus AD times BC equals the product of the diagonals. So the sum of the product of opposite sides equals the sum of the product of the diagonals. And you can use this for one of the homework problems. I know we didn't get to the last problem for class. That's okay, you can just do it later. Yeah, so we'll have all of the handouts and the homework on the website, and we'll be posting the keys sometime during the week, but we don't know for sure yet. Anyways, thank you so much for coming. Next week, we have the same times and the same schedule, so be sure to come to that. Isabella, anything else?
Thank you guys for showing up. This is our first time, and I'm glad it went so well. Thank you guys. Bye.
Thank you.